In the last video, we showed that if we mixed this mass of ice at this temperature with this mass of water at this temperature in an insulated cup, we would melt all the ice after warming it up to zero, and that there'd still be heat left over. So as we said in that video, that sort of preliminary work is needed before you can actually do anything to quantify what the final temperature is. Well, now that we know that, let's go ahead and do that work. And what we're going to do is set up a general symbolic solution before we plug any numbers. I always recommend that. Let's get started. All right, so we said the ice was going to warm up to zero from -20. Then it was going to melt, and that was going to take some heat. And then that melt water from the ice is going to warm up, and all the heat necessary to do these first three things is going to come from the hot water, which is going to give off heat as it cools. So we've got 4 terms, and the number of terms is going to vary by the type of problem that you have. Okay, so there could just be 2 heat terms, or there could be 4, 5, or even more. Notice that all these heat terms have to total to 0 because we're inside an insulated cup, and so no heat is gained or lost or exchanged with the surroundings. It's all just internally exchanged from being given off by the hot water and into the ice. Now, when you're developing an algebraic solution, you want to make sure that all the symbols you have are numbers that are either the unknown you're looking for or parameters that are given. And you also want to make sure that you label quantities that are different with a different variable. So here we have delta T for the ice as it warms up to 0. That's different from these other delta T's. So you want to use a lot of subscripts to make sure you don't write one symbol for something that's going to have different numerical values. See, these delta T's, those aren't actually given in the problem, and they're not something we can look up in a data table like the heat of fusion. So we need to actually make these more specific and put it in terms of what's given in the problem. So here I've rewritten it using things that are actually given in the problem. So we have the mass of the ice, the specific heat of the ice, the delta T of the ice. Deltas are always final minus initial, so we've got the final temperature of the ice is 0. The original temperature of the ice. Then we have the mass of the ice divided by the molar mass of water to give us the moles of ice times the heat of fusion, so that's going to give us the melting heat. Then we have the mass of the ice times the heat capacity of liquid water, because now that the ice is melted we have to use that specific heat, times delta T, which is going to be the final temperature, so I'm using T sub F as final temperature, minus the initial temperature of the melt water, which was 0, that's where it melted. And then we have the heat term for cooling off the hot water. So it's the mass of the water, the heat capacity or the specific heat of the water, and then delta T for the hot water, which is the final temperature minus that's a T sub H for the initial temperature of the hot water. Okay, so if we look at these, we're putting heat in here, here, and here, and we're taking heat out of the hot water, so we're going to end up having 3 positive terms and 1 negative term, and that's going to give us it's going to total to 0. All right, now if we look at this expression at the bottom, everything in here is either something we can look up in a data table like the heat of fusion, or it's a number that's given in the problem. So then, and the last thing, of course, is T final, which is the unknown. So we've got it in 2 places. So our task is simply to solve this equation for T final. Let's start by distributing the things that are outside those parentheses. So we're going to multiply expand each of these parentheses. We did that, and we had several places where we're just multiplying by 0, so those dropped out. So we have this, and so now we're going to group the terms that have T final on the left. So we've got T final term here and here. We'll keep those on the left. We'll move everything else to the right. Okay, so we've kept the terms that include the unknown T final on the left-hand side. We've got everything else on the right. Okay, so we can see that if we just take this part here and divide both sides by it, we'll have solved for T final. We have our algebraic solution. Let's examine it to see if it makes any sense. So if we look at this, this is going to have units of joules, this has units of joules, this is going to have units of joules because we have moles here times joules per mole. So we can get joules on the top. Whenever you add terms together, they have to have the same units. So you can always check your algebra that way. So make sure this term, and this term all have the same units. So we have joules. On the bottom, we can see we've got mass we'd have that in grams. This specific heat could be in joules per gram per degree C. So we've got joules per gram per degree C times grams. So we've got joules per degree C. So joules divided by joules per degree C is going to give us units of degree C, which is what we're looking for. So always do that check when you have an algebraic solution. The second thing to do is see if it makes sense logically. So let's look at this. We have a temperature. This is the temperature of our ice. Notice the higher this number is, the higher our final temperature. That makes sense. Same thing with the hot water. The hotter the water is, the higher this number is going to be. In actuality, we know this number was actually a negative number. So that means this term, the more negative this number is, the more negative this term is, and that's going to eat away at our final temperature. Okay, on the other hand, the opposite's true for our hot water. Makes sense logically. If we look at this term over here, this is another negative term. So the bigger the heat that we have to sink into the actual melting of the ice at 0 degrees C, the lower this temperature is going to be. Also makes sense. Great. So the answer makes logical sense. Let's go ahead and plug numbers in. Okay, so we've plugged in numbers to match all our things that we can either get from our problem or constants like specific heats that we can look up on an equation sheet. Of course, the heat of fusion as well. Okay, so let's cancel our units. So we can see we've got grams and grams and grams and grams and grams and grams. We've also got degree C with degree C. And I guess I'll go ahead and cancel this mole with this mole. So we end up with just joules, joules, joules on the top. Let's cancel grams here as well. So we end up with joules on the top, joules per gram, or joules per degree C on the bottom. So we end up with just degree C. And if we plug in those numbers, we get 2.8 degrees C. That seems like a reasonable number given the amount of ice we have and how cold it was. I know that seems like a lot of work and it took a while, but I wanted to explain all the steps, and I do urge you to follow these steps each time you do a problem to make sure that you're first identifying the phenomena, then doing algebra, then checking your algebraic solution for logical consistency and for units, and then plugging in numbers. So notice plugging in numbers was the very last step, and so it should occupy maybe 10% of your effort. If you put a lot of effort in the other things first, then the number will end up making sense.